Welcome, guys. Yeah, so this is the video about the pseudo theorem application and also the so-called classification of the small group. Okay, so in the previous video, if you haven't seen it, then I will post the link below. So in the previous video, we just solve all the finite group, classify all the finite group up to order 15. And I say I left it with 12 because 12 computation is a little bit difficult. So in this video, let's finish this 12 classifications. Okay, so let me just write the results. I will give the formal proof. And some of my friends say that my writing is a little bit not very clear. So now I try to write every step clearly. Okay, hope you guys subscribe to my channel. Okay, so our goal is when we have the orders 12 group, and we know that if it's abelian, then it must be direct sum of cyclic. So easy to show that C for direct sum C3 or C2, C2, C3. Okay, so we are only focusing on the non-abelian group. Okay, so we have three choices. One is so-called D6. Okay, so D6 is basically AB generated by AB, where A6 is 1, B squared is 1, and the BAB inverse is A inverse. Okay, and we have so-called T group, which is a little bit strange. AB A6 is 1, and this is B cube. Sorry, let me just, I think this is not correct. Yeah, I think we have B squared is A cube, and the BAB inverse is A inverse 1, and also the third one is the A4, so which is alternating group with order 4. Okay, so even permutation. Okay, so our theorem basically so theorem is basically if G is 12 and non-abelian, then G must be A4, T, or D6. Okay, yeah, so this is our main results in this video. Okay, yeah, so let's do it. Okay, so the proof will be a little bit longer, and I hope to do it step by step. Okay, so now start with 12 and the my assumption is non-abelian. So I can take, so by the, okay, so the first one is by the pseudo theorem. By the pseudo theorem, there is this pseudo 3 group. Right, there's pseudo 3 group P, which is order 3. Okay, and so I can consider group action econ G quotient P, where P is basically XP, where there X belongs to G, right? So this is a group action. So my group action is very simple. Somebody give you a G, you just act on the left multiplication. So GXP will be GX and P. Okay, so this group action will construct a homomorphism, right? We'll construct homomorphism from G to symmetric group with the order G modulo P, right? Because this G modulo P is the index is 4, because 12 divided by 3 is 4, right? So this is actually S4. Okay, so we have a group homomorphism from G to S4. And notice that the kernel, right? So we have a kernel. So kernel will be a subgroup of G. Okay, will be normal subgroup. So kernel rho is a normal subgroup. of G. Okay, so the key, right? So what's the kernel? So kernel means that in G module in S it become a trivial map, right? So it must satisfy the let's say if G belongs to kernel, then it must satisfy the GXP equals XP, right? For all X, right? So let's say if I choose X to be 1, right? So it must be GP equals P. So that means G must belongs to P, right? So this tell you that the kernel row must a subgroup of P. Okay, so in general, this is hard to solve, right? But in this case, that P is just the Sigley group with order 3, right? So that means we only have 2 cases. Okay, so first case is that the kernel row will be 1. Okay, and the second case is kernel row will be P. Okay, so let's separate into 2 cases. Okay, so so we have 2 cases. So kernel row is 1, kernel row is P. Okay, so if kernel row is 1, that means row to GS4 are basically injective. So G will be identification by the first isomorphism theorem. So G modulo the kernel, which is identity is isomorphic to some subgroup of S4. Okay. Image row will be a subgroup with length 12. Okay, so the theorem which related to the symmetric group is that the only index 2 subgroup of A4 is S4. Of S4 is A4. Okay. Yeah, there are 2 ways to prove it. So let me just quickly say one way. Okay, so one way is that so in a S4 you have 5 different of element, right? One is identity, one is so-called 2 permutation. So it's like this. Okay, so this is 1, and I think this contains 2, 3, right? And then I think you can change its 1. So you can take, so I get 1, 2, 3, 4, right? So you can take, this is 1, 3, 2, 4, and 1, 4, 2, 3, right? So yeah, this is one type, and then you can also get this 1, 2, 3, 2, 3, 1, 2, 3, 1. And yeah, and also you get 1, 4, 2 or 1, 2, 4 or some kind of like this, right? So there's a 1 is that you didn't change your element, and then you permute all the element, and then you permute 3 of the element, and then you get the thing which you permute. Yeah, so let me see how to see this. Right, so S4 has 4. Let me see. 24, right? I think it's the 4 conjugate C class. So 5 conjugate C class. So 1 plus 6. So 1 plus 3 plus 8. So this is 1, right? It's 3 of them. And then for 2 permutation, you get 6 of them. And then for another permutation, you get 4 of them. And also you have so 24 is 1 plus 3 plus 8 plus 8, 6, right? And this, let's see. Yeah, right. So this is identity. This is 2 permutation, 2 side 1, 2, 3, 4. And this guy 8, I guess comes from this type of permutation. And the 2, 6 comes from this. It has odd or even permutation. Okay. So now A4 is a subgroup, normal subgroup of S4 because it's index 2, right? So it must be if a normal subgroup contains 1 element, then it must contain all the conjugate elements. Okay, so that means you need to find something which is total contains 12 elements. So the only guy which contains all the 12 elements is this guy. right? So this is 12. So it must contain the identity. Also the element 3, so which is 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. These are all even permutation. And now you get 8. Yeah, I think these 8, these 8 must come, I guess it must come from 1, 2, 3, and 2, 3, 1, right? So these are all even, not 2, 3, 1, 1, 3, 2, and all the other pair. Okay, so these are all the elements that the A4 gets. Okay, so from here, you get the answer must be A4. Okay, so G must be A4. Okay, so now you can see that the remaining case. So the remaining case is a kernel row, which is a P. Okay. So here I tell you that the P is we get kernel, right? So P is a normal zero 3 of G. Okay, so if rho is if P is normal zero group G, then by the theorem we know that the P is the only zero. And then we know that the normal that you will so all right, P is the only zero 3. Okay, so now the problem is that now the problem we can use this to get the largest order of the element in the group. Okay, so we can use this to find the largest. We can use this constraint to find the largest order element in the group. Okay. Okay, so that means if C belongs to P, so C has at most 2 conjugate C class. Right, because P is the only P is right, P is the only so P is normal, right? So and only one of these, right? So C at most have 2 conjugate C class. You can work on a centralizer. Right, so the centralizer, which is group G belongs to G, where GC is CG. Okay, and by the theorem, this will be G quotient the orbit of C. Quotient the conjugate C class of G. Okay, so the conjugate C class of C. Right, so this guy is the centralizer. Right, so C at most have 2 conjugate C class, right? So which tell you that the CGC is at most right 6 or 12. Right? Okay, so then by the CO theorem, I get there's a one element which is order 2, right? So there is element D in a group this group G and this CGC, which is that D square is 1. Okay. And also right, have this. And I know that the C is the BP. This is the element of P, right? So C cube is 1. Okay, and the D inside CGC, so we get CD equals to DC. Okay, so now we have D squared equals to 1, C cube is 1, and CD equals to DC. Okay, so that's that A to be CD. So C is just inside P, right? And D is the order 2 element in the CGC. Okay. So obviously from here that one can check that A6 is 1. Okay. So A has order 6. Okay, so here comes the yeah. So this almost up to here that we already 90% finish, right? Because we already get something which is order 6 up to 1. Okay, so remaining is to get at least B. Okay, so now it's very easy. Let me just finish the final thing, right? So I can let A to be generated by this element A, which is a subgroup of G. So subgroup of G, and this is order 6, right? So you can take a B belongs to G, Okay, and then this B belongs to G, it must have, right? So your group G can written as a 1A, A squared, A cube, A4, A5, and then B, BA, B squared, BA3, BA4, BA5. Okay. Right, this is, so all of these are, they are different, or they are different, right? So you can ask, what is B squared, right? Okay, so by this, we know that BA has index 2, right? So B squared must be, yeah, we can ask the B squared, well, what is the B squared? Okay, so let's see, I think we don't need this. Okay, so what is the possible B squared? Okay, so let's do it step by step. Right? So obviously B squared cannot be this, right? B squared cannot be all of this, right? If B squared equals to BA something, then I will get B equals to A something, which do not make sense because I take B outside A. Okay, so B squared cannot be this, right? It must be one of these. All right, so B squared can at most be 1A, A squared, A cube, A4, A5, right? Okay, so B squared is one possible case, right? Possible. But B squared A is not possible, right? If B squared is A, that means the whole group G is generated by B, which will be cyclic. So this is not possible. How about B squared equals A squared? Is it possible? Is it possible B squared equals A squared? And you can check that this is impossible. Okay, so the reason is that I know that B squared compute with B, right? So if this is the case, then that one can compute that BA squared B inverse, right? Which is let's see. Okay, so let's keep this as a question, right? So we got B squared, maybe A cube, or B squared maybe A4. Right? B squared cannot be A5, right? If B squared is A to a 5, then B squared will be A minus 1. It's the same that the whole group is G is generated by A minus A inverse, right? So the only possibility is that we get these. So now we have four cases. Okay, so we have possible. So we have possible case. Our B squared equals to 1, or B squared equals to A squared, B squared equals to A cube, B squared equals A4, right? So these are all the possible cases that we have. Okay, now BA has index 2, right? So that means that the B inverse should be in A, right? Because B is normal, right? So BA must be AB. So you take A here, and then you inverse it, then you must get something which is inside A. Okay. So now we can ask the same problem, right? So BAB inverse can be 1. BAB inverse can be A. BAB inverse can be A squared. BAB inverse can be A cube. BAB inverse can be A4. BAB inverse can be A5. Okay, so now we can admit all these possibilities and check where it remains or not. Okay, so this is impossible, right? Otherwise, that A will be identity. Okay, this is also not a case. Otherwise, that AB commutes become abelian. Okay. Okay, so somehow like this is the only thing we can get. Right? But remember what? Remember that this BAB inverse to the power K, right, will be BAK B inverse, right? So this guy can at most have order 6, right? So now let's say if BAB inverse is A squared, right? Let's do the third, then you get A6, which is BA cube, B minus 1, right? And this is 1. If this is the case, then A cube will be 1, right? But A cube this should not be 1. A6 can be 1. So this is impossible. Okay, and you can check that if you use this, and if you use this, then if you do the cube, then if you do square, then you get contradiction. Right? This is also impossible. This is also impossible. Right. So the only possible case is that BAB inverse is A minus 1. Okay. Okay. So final is that we have BAB inverse is A minus 1. And so what is the possible cases of B squared? So what's the possible B squared, right? So we just get B squared is 1. It may be possible B squared equals to let's see. So A cube, A squared, and A cube, and A4. Okay. Yeah. So these are guys that may be possible, right? So by the previous table, right? Previous table results, we know that the only possible case is B squared equals to 1 and B squared equals to A cube. So let's see what's going on. Okay. Okay. So only these two are possible. Okay, and the reason is that let's start from here, right? So suppose this is A squared. Then we get we start from here, right? So we get BAB inverse is A minus 1, right? And then we can square it, so we get BA squared B inverse is A minus 2. Okay. But A minus 2 is B minus 2, right? So B minus 2. So we get the BA squared is B minus 1, right? Which so here you get B squared A squared is 1, right? So you get B to the 4, A to the 4 is 1, right? Which is a contradiction because A at most A6 can be 1, A to the 4 should not be 1, right? So you start from here, and now you say, I think you square it, and then you change this to B minus 2, and you cancel this B minus 2, you get this. So you cancel this B minus 1, and you get B minus 1. So you get B squared A squared is 1, but B squared is A squared, right? So A to the 4 is 1, which is contradiction. So this cannot happen, and also you can check that this cannot be happen. Okay, so the only two cases are these two. Okay, so combined with the previous results that we just proved, we just very happily proved that these three are the only non-abelian group of the order 12. Okay, so hope you guys like this video. Subscribe to my channel. Bye bye.